In this example, we'll look at how to enter our data and for an analysis of variance, which procedure to use in SAS, and then also how to test for homogeneity of variances. So in this example, the mean dissolved oxygen contents measured in parts per million of 3 different lakes were to be compared based on independent random samples of 10 observations taken from the center of each lake at a depth of 1 foot. Use the SAS commands below to conduct an analysis of variance and to conduct Levene's test for homogeneity of variances. So in this example, our lakes are 1, 2, and 3. Lake 1 observations are in this first column, Lake 2 observations in the second column, and so on. When we look at how to enter this information into SAS, so I can't get all of it on screen here at once. I want to take the information in this data table and enter it into a data set. So our SAS code begins here with the display manager command. So we clear the log lines, our ODS results, and reset everything. Anything in your program here that's uppercase is a SAS command. Don't change how it's spelled or punctuated. Anything that's lowercase you can change to make problem specific. So in this case then, the display manager commands are all part of the SAS, and then we have a data step. When I talk about data step, I refer to the data statement, the input statement, and data lines. Those 3 things go together. The name of this data set is called 1, so you can use anything you want here for a data set name. The first character must be alphabetic, then the rest of it could be numerals if you wanted those, so some kind of an alphanumeric code for the data set name, the first character being alphabetic. Likewise with the variables. There used to be an 8-character restriction on the variables. There no longer is, but again the first character is alphabetic and then the rest of it can be alphanumeric. You want to avoid any special characters or spaces in a variable name. When it sees a space here, that indicates that we have 2 different variables. If you want the kind of the illusion of space, you can use an underscore. An underscore is the only special symbol you can use in a variable name. What this means is that we're creating a data set called 1. In this data set there are going to be 2 columns of information, lake and oxygen. So the order we specify on this input statement has to determine the order of the data that occurs on the line after data lines. There are 2 variables here, so SAS is going to look for 2 pieces of information on every line after the data lines. The first piece of information will be lake, the second piece of information will be the oxygen measure. There must be at least 1 space separating these pieces of information for this input statement to match up with the data in this format. Now then, so this 1 space 0 refers to this Lake 1 observation 0. Then 1 space 2 is Lake 1 observation 2, etc. And so we go all the way through this until we get to the second lake, first observation, and then we continue down through the last, Lake 3 observation 30. So where you see this ellipsis, you would continue filling in all of the other information until you have all 30 lines of data input. You don't have to put a semicolon on a line by itself after the data, but it's usually the recommendation. So the yellow highlighting here behind the numbers, this refers to the data. Notice our data are not punctuated, only SAS commands are punctuated with semicolons. After we've entered the data, we can use a print procedure. Data equals 1, and we want then to include lines of title that appear at the top of the page. And so in quotation marks, either single quotes or double quotes, we write the title here, Analysis of Variance and Levene's Test Example. And you can put your name on your output if you want. You can have up to 10 lines of title, the first being title, then title 2, all the way to title 10. The outcome for this print procedure occurs on page 2 of this handout. So I'm just repeating here in red and what's going on. So the print procedure merely prints the contents of a data set. It gives you an opportunity to proofread your data when the data table is not too large. It does not activate SAS output to be printed or anything like that. It merely prints the contents of the data set, such as we see here. Scrolling back to the top, it creates a column for observation number as well as the variables you enter. So this observation is default and goes 1 through last, and then you can check in the lake columns and the oxygen column that you have the right data entered. If you have a very large data set, proc print would not be recommended because it would just take an enormous amount of pages to print out those results. So the print procedure, as long as your data set's not too big, it gives you an opportunity to proofread your data, and that's all it does, is just print a list of the data. What we want for the analysis of variance procedure is a procedure called GLM. The GLM procedure produces an analysis of variance table, and we're going to look at several things here. We tell in the procedure, the same as the print procedure, that we want to operate on which data set. The data set we created up above was called 1, so data equals 1. Just as a minor note here, whenever you create a data set, there's no equal sign here, just at least one space. When we call the data set, we use the equal sign. The plots equals and then the information in parenthesis, all of this is an option. At this stage in the course, if you want the plots, then I would tell you to print everything here or include everything here in your proc GLM statement. Okay, so it's an option, so you can, as with any option, you can opt to use it or opt not to. To get an analysis of variance table, at a minimum, we need the following. We need the proc GLM statement, the class statement, and the model statement. We can get by with fewer statements, with as few as those 3 statements. Okay, that will give us the analysis of variance table. And then we'll talk about the mean statement shortly. So just given the proc GLM, class lake, and the model statement, we'll look at the output. This begins on page 3 of the handout. And so it tells us right here the GLM procedure. The remarks written in italicized red here, that's me talking back to you. Okay, this is the result of the class statement in the GLM procedure, and it tells us that our class variable was lake and how many levels it has, when there were 3 levels and we had 30 observations. If you'd made a typographical error, say when entering the lake information, and you'd had a lake 4, that you accidentally struck the 4 instead of, say, the 3, then you would have 4 levels, and you'd see that information here. So this, again, is an opportunity for you to proofread your data. The model statement is what produces the analysis of variance table. So the model statement then is always of the form response equals treatment. And so you want to make sure that you get the order there correct. Our lake here was numeric values, and so if we said lake equals oxygen, we would get an analysis of variance table, but it wouldn't make any sense. So it's always of the form response equals treatment, and then punctuated with a semicolon. It says here at the top what our dependent variable is, and that was the oxygen content, and then we have our analysis of variance table, just as we discussed in class. Where we saw treatment before, we see the word model. This degrees of freedom 2 comes from the treatment degrees of freedom, which there were 3 treatments, so 3 minus 1 is 2 for the treatment degrees of freedom. The error degrees of freedom is 27, and the total degrees of freedom is 29. We had a total of 30 observations, and so we know we should get a treatment minus 3, a number of observations minus 3 treatments for the error degrees of freedom. And then the computation of the sums of squares. Note the sums of squares divided by their corresponding degrees of freedom yields the mean squares, and then the mean square treatment divided by the mean square error gives us our F statistic. And then the p-value here, if we see a value less than alpha, then we know we're rejecting the null hypothesis. Even though we're looking at the analysis of variance table up here, I want you to get comfortable reading the information down here in this last part where it says type 3 sums of squares. We're going to be looking at more and more elaborate types of models in this course, and the information we need will always be in this bottom one, this type 3 sums of squares, and this will always stay fairly simple up here and won't give us the most detailed information. So get in the habit of reading the type 3 sums of squares. A type 3 analysis, this has nothing to do with type 1 error, type 2 error, and that sort of thing. A type 3 analysis for the purposes of this course is that comparison of the treatment level means, or the comparison of population means. That's a type 3 test. And so you see that this information that's written here for Lake exactly matches the model information given at the top of the page in the analysis of variance table. So that if we were to write a conclusion here, our conclusion would be that there is a significant difference in dissolved oxygen content among the 3 lakes, but it doesn't tell us which one is different. So that's our analysis of variance table. The results of that plot option that I gave you at the top, we'll reduce this a little bit so I can get it on screen. On page 4, the plots we've requested were the residual diagnostics, and so we're interested in these plots that occur here on this first column. In the first image up here in the upper left, what we're looking for is a random scatter about 0. We see we kind of have a funnel shape. That means that the residuals tend to get larger as the predicted values get larger. So we're looking pretty much, in our case, Lake 1 and Lake 2 and Lake 3 had a large dispersion. If you take a regression analysis course, you'll do more with the information on this side of the residual panel. In the second row, first graph, the residuals on the vertical axis, the quantiles down here. Sorry if I leave the mouse hover, it wants to prompt for another message from SAS talking to my computer, so that's why what you keep seeing flickering in yellow. What we're looking for here in this second image is that our data points indicated by the zeros or the circles in this plot is that our data points coincide with the reference line at 45 degrees we see in here. And so that if your data departs from that line, it's an indication that it's not normally distributed. Then also we have this information about the last, in the last row, which talks about the distribution of the residuals. Remember, we have an assumption that our errors are normally distributed when we write the model, and this is what we're testing. We're recovering those residuals, plotting them, and seeing if they have a normal distribution. So it doesn't look exactly normal, but it does look symmetric, and that's actually works okay for us. So this is the residual equals diagnostics then in our plot commands here. And so just these remarks in red indicate or reiterate those things that I just said to you. Non-normality doesn't appear to be a strong issue. We'd probably want to investigate the equal variance assumption first. Let's go back to the program on page 1. So what I've shown you so far is the result of the GLM procedure, the class statement, and the model statement. We haven't talked about the box plot yet. We'll get there. We'll also look then at the means for each level of lake, and we're going to look at a Levene's test, and it's going to be that operates on the absolute residuals. And so that if we move then to pages 5 and 6, page 5, we get this box plot that was requested. It's actually a default image, and so that we get we'll get this box plot that reflects the means of our 3 lake variables, and then also includes the information here from the analysis of variance. We see that the values here are very compact, close together, if we remember information about box plots from our first course, and so that the variability here is similar to the variability we see here. And then for Lake 3 we see observations that are more spread or more dispersed, indicating a possibility for unequal variances, and so we can formally test that and we use Levene's test to do that. So that mean statement that we saw on page 1, the HOV test equals Levene with the type equals ABS option, produces the following ANOVA table. So it computes the absolute residuals and conducts an analysis of variance on the absolute residuals. And so we'll see that the degrees of freedom here match the ANOVA from the page 3, or the first page of the ProcGLM output that we looked at. The sums of squares and mean squares are different because these are, again, the absolute residuals. And if we're a 0.05 person, we would find that there is significant heterogeneity of variances. And the analysis of variance table that we read back on page 3 is really not valid. We needed to come up with another approach to analyze our data. And then the plots equals box plot. This is actually another box plot we can get. Notice it doesn't have the analysis of variance F test in it. This is a redundancy in SAS. Hopefully that gets addressed soon. You can also request just the mean statement lake, and anything that slash we saw with the HOV test with the type equals ABS has been deleted here. We can request just the means for lake to be printed. In addition to Levene's test that we saw above, we'll get this information, and you'll get the sample sizes for each of your lake levels, and then it will also give you the Y bars and the individual standard deviations, or S's. Note that the pooled variance estimate or pooled standard deviation estimate is not here. It's the information pooled from these three things together that compute the mean square error. And so the box plots indicate to us that this lake 3 has a higher variance. Here we see that larger standard deviation in comparison to what's going on in lakes 1 and 2, and we find that is significantly different. So again, you can take this mean statement, means lake, and we can scroll back up to our program. And instead of adding these options on the means lake, we could just put a semicolon there. So the slash and the options that follow then are things we can choose to use, or again opt not to use. Again, just a reminder, make sure that you punctuate things as I have shown in the handouts. I include spaces. The actual uppercase, lowercase thing doesn't make much difference for what we're doing. Whenever I communicate to you and show you a template for a program, whenever you see uppercase, I'm letting you know things that are SAS commands. Anything that are lowercase are things that you change to make problem specific. When we refer to the data up here, important notes to remember. The input statement, it specifies the number of variables and the order they occur after the data line statement. Here's the important piece of information. SAS assumes that all the data that you enter are numeric unless you say otherwise. So suppose our lakes were some character value, some bit of text. Well, we'd have to use a single word to denote what each lake was. So but for simplicity, let's just say they are A, B, and C instead of 1, 2, and 3. If you want that to be recognized, then you need to follow this word lake by a space and a $sign. What that does is that indicates then that your lake variable is character. That's what the space and $sign does. You don't want to put spaces in there or multiple words. So here we have a lake near town called Lake Carl Blackwell. And so those 3 words, if we were to put that in for the lake, that longer text, that would not work because of the spaces in between the words lake and Carl and Blackwell. So you want to make sure whatever you choose for text here is one single word, and put the space and the $sign on the input statement. The input statement is the only place you'll need that $sign. So once you get that to read in, then you don't need to put it in any other time you invoke the usage of the lake variable or the character variable. Now, from a statistical perspective, the next thing is what we did find out is that we do have significant heterogeneity of variances, so that invalidates that analysis of variance F-test we have for the oxygen content. So we'd need to look at another example, and we'll pursue, well, what happens when we don't have the data that are normally distributed. If Levene's test indicated that data, your treatments have homogeneity of variances, then it's valid to read your analysis of variance that comes from the model statement. If it doesn't, we need to modify our program so that we read an appropriate output given the conditions we have.